you could just write. Okay, so yesterday we were working on this. We're comparing two hypotheses, looking at the amounts of different elements in a compound. We're trying to figure out between these two hypotheses, are all atoms of, bless you, are all atoms equal mass, or do different elements have different masses? That's the idea. So I wanted to run through so we have kind of an answer key to start. And I'm going to pause the video. We're going to finish, and then I'll do the end. But so we had these two compounds. They both contain carbon and oxygen. Compound A has 57.1 grams of oxygen and 42.9 grams of carbon. So we divided that, and we found that that ratio, that mass ratio, is 1.33. Okay. On compound B, 72.7 divided by 27.3 grams came out to be a ratio of 2.66. I gave you some different decimals, and I said, hey, it's handy to know the fractions these make, like 0.25 is 1/4 or 1 over 4, 0.5 is 1 over 2, 0.75 is 3 over 4. And I said it's also helpful to know thirds, like 0.33 is the same thing as 1/3, or 0.66 is the same thing as 2/3. Okay? So question B, if I compare these two mass ratios, I can see that B is 2 times as large. All right? And then for C, we expressed them as improper fractions. So this is like saying 1 and 0.3. So it's like 1 and 1 over 3. Okay, we converted that to an improper fraction by taking the denominator times the integer and adding the numerator. So 3 times 1 is 3, plus 1 is 4, and then keep the same denominator you had originally. So it's 4 over 3 for A. And then for B, this is the same thing as 2 and 0.66, or 2 and 2/3. If I do the same thing, 3 times 2 is 6, plus 2 is 8 over 3. So those are the improper fractions. Okay? We had all that. We did that. So we came down here, and using those ratios, depending on how you want to do this, there's a couple different ways you can do it, but I'm going to write it down here. So we had this ratio on A is 1.33, or 1.33 to 1, same thing, or 4 to 3, and that's oxygen to carbon. And I did some models, and I made black dots be carbon, and I made white dots or circles be oxygen, which is cool because it looks like O, right? So if all of them have the same mass, like maybe they all have a mass of 1, according to hypothesis 1, that would be 4 white dots stuck together, and then 3 black dots attached to them. This ratio down here for B was 2.66, or 8/3. So if I did that, to keep the masses working out right, I would have 8 circles, so 8, yeah, stuck to 3. So that mass ratio would make sense. That would be an 8 to 3 ratio. All right. Then in hypothesis 2, it says they're not the same. Atoms of O are heavier than C. So the way we did this was we made a C dot, and then we made a larger dot. And you could do it like one of them is a mass of 4 and the other is a mass of 3. That would work. I used that 1.33 ratio. I said the smaller one's 1 and the larger one is 1.33. So that would work. Sorry, I'm going fast because kind of talked about it. And then the second one, I could also have done, it would have worked the same way. If instead of 1.33, I had done it this way. That would also work because 1.33 to 1 ratio is the same as a 4 to 3 ratio. We just changed the format of it. The 4 to 3 kind of helps when we're drawing these over here. All right, then at the bottom down here, we got to say, all right, now we need a ratio that's really twice as much in terms of oxygen. So we figured out we could do something like this. Keep the oxygens the same as they were before. So now I've got a total of 2.66 to 1 ratio in terms of mass, right? Okay. So we can look at those and kind of start to think, hey, this one seems to make more sense to me. And your answers in terms of which hypothesis you like better, I mean, it's kind of your own opinion at this point when we get to number 2. But we'll see what you think and why you think it. All right, so on number 2, we did the same thing. 79.9 divided by 20.1 came out to be like 3.9 something. It was easier to just round that to 4. And so you guys can check these because we never went over these together as a class, so check your own. And for B, it came out to be like 88.8 divided by 11.2 was like 7.9 something. So we made that 8. So we see again for B, B is 2 times larger. And expressing these ratios as improper fractions, anytime you have a whole number, it just means that number over 1. It's the same thing. So for A, it would just be 4 over 1. B would just be 8 over 1. Good so far? Okay, so we said that in A, and this is different. This time it's the ratio of copper to oxygen, right? Isn't that right? And so the first one was 4 to 1, and the second one, in terms of copper to oxygen, was 8 to 1. So again, if all atoms have the same mass, then when I draw this, I would just do 4 black dots stuck together, and then I would do 1 white dot. Okay? Oh, I didn't write the formulas. I forgot to write the formulas on those. But what would this be? So we've got Cu, and how many of them? 4. And we have O, how many of those? Just 1? If there's just 1, do we put a number after the symbol? No. Okay. Down here, it would be 8 coppers to 1 oxygen. So, oops. 1, 2, 3, 4. 1 oxygen here. 1, 2, 3, 4. All right, and that would be Cu8O. Right? So it's saying that there's copper, there's 8 of them. Oxygen, there's just 1. But then if we go over here to hypothesis 2, let's say instead the 4 to 1 ratio is really because copper is maybe 4 times as massive. So I would do like a big black dot. That'd be my copper, and I'd say that has a mass of 4. And then I've got a white dot for oxygen that has a mass of 1. and that would work out. That would give me a 4-to-1 ratio. It's saying it's not that we have more atoms of copper and that they're all the same mass. This time in hypothesis 2, we're saying that copper just has a mass that's 4 times greater. Bree. Okay, so we had a student that had 2 bigger circles, made them each worth 2, and then 1 oxygen that was 1. So let's see how that works out. Can we do that? All right. Now, in the next one, we say it's an 8-to-1 ratio. So to compensate, oh, that, by the way, is Cu, there's 1, and O, there's 1. This over here would be Cu2O. All right. And then here we did, well, let's just say there's 2 of those 4 mass particles. Okay, so what did you do over, and that would be Cu2O. And what did you, and that would be an 8-to-1 ratio. 4 plus 4 is 8, 8-to-1 in terms of copper to oxygen. So what did you do over here for this? Huh? I mean, you could have, you're showing that they have different masses, so that is acceptable. But we just have to make sure the next one you draw has twice as much. So your next one would have to be like this. So these would each be 2. And this would be 1. That would still give us an 8-to-1 ratio. Okay? But that would be Cu4O. All right. But this is what I did here. Yep, because then you're showing the ratio of oxygen to copper is 4-to-1, but it's actually copper is 4 times more massive. Okay, so here's where we get to discuss something here. Which hypothesis seems more reasonable to you? Justify your answer. Anybody want to share what they put and why? You put hypothesis 2, why? Okay, so you said 2 clean, not so messy. Anybody else want to share? You can't say both. Why? Because one hypothesis is saying that all atoms have the same mass, regardless of the element. So atoms of hydrogen have the same mass as atoms of oxygen, or in this case, atoms of copper have the same mass as oxygen. Hypothesis 2 is saying, no, that's not right. They have different masses. So they're competing hypotheses. So you can't say that you agree with both. Anybody else want to share? Anybody hypothesis 1? Okay, why'd you say that? Easier just to understand it, just to see there's 4 coppers, there's 1 oxygen, just draw the dots, put it that way, okay? Well, when we were looking at the stuff, we were talking about Avogadro's hypothesis. One of the things that was pointed out there when we were looking at that, like the combination of hydrogen and oxygen, for example, is that things combine in simple whole number ratios. So what I'm going to do right now is I'm going to ask you to get out some paper. We are going to be doing some notes today, but we're going to do a little example there and see what happens. So if you could take out a piece of paper, and we'll call this title it at the top, Notes 131. Okay, so yeah, we can just call this, oops, Notes 131. We're going to do something here, a little activity maybe that'll help us understand the difference between hypothesis 1 and hypothesis 2. Maybe make it a little clearer in terms of our choice of which one we think is the right one. And we're going to do this example, then we're going to go back to the worksheet, and then we'll add some notes to this later in the hour. Okay? So I'm going to erase that at the top because I'm going to have to scroll a little bit here. But we have two compounds. They both contain oxygen and hydrogen. Okay? The first compound, compound A, has 94.1 grams of oxygen and 5.9 grams of hydrogen. The second compound has 88.9 grams of oxygen and 11.1 grams of hydrogen. So just like we did on the worksheet yesterday, can you figure out the mass ratios for me real quick? So video paused here. So the mass ratio of A was 15.94. Should we keep it like that, you think? Round it off to 16. That'd be a little easier to work with, maybe. And what about in B? It's like 8. Did you guys all agree? Anybody disagree with 8? Okay, so if it's 16 and 8, let's look at letters. So let's do our little models. First, we'll model each compound. If all atoms have the same mass, this is hypothesis 1. All atoms, same mass. I just shortened the sentence and made it grammatically incorrect. But so in compound A, we had a 16-to-1 ratio of masses. That is oxygen to hydrogen. In compound B, oxygen to hydrogen was an 8-to-1 ratio. So go ahead and do a model of those. Let's see what you get for that, and then we'll talk about that. I'm going to pause the video again here. Okay, so how can we do compound A if all atoms have the same mass? You know, or you're confused? Okay, what did you say? So 16 white circles? What do those represent, those white circles? So you made oxygen be a white circle, and you made hydrogen be filled in. So your model, if it's a 16-to-1 ratio, might be something like this, with 16 white dots and 1 black dot. Okay. And what about compound B? You did 8 of the oxygens. And 1 of the black dots. Okay, so if hypothesis 1 is true, then that's what those compounds look like. We have, formula-wise, if we wrote it, would be like O16H, and then this one would be O8H. Everybody agree with that? All right, so guess what we're going to do next? We're going to try to model them. If the atoms have different masses, how can we show those ratios? Okay? That's hypothesis 2. As you can see at the bottom of the screen, is coming up. I'm going to have to scroll up, though, which means I'm going to have to erase this. Can I erase it? Everybody got it? One's 16 white dots. However you draw, it doesn't have to be exactly the same as mine. Could have just did a row of 16 white dots with a black dot at the end. Whatever. And then the second one is 8 white dots and 1 black dot. All right, so now we're going to say, well, what if it's hypothesis 2 instead? All right, so I'm going to go ahead and pause the video again for a minute here while you guys go ahead and try to do hypothesis 2. Again, we have model A is oxygen to hydrogen is a 16:1 ratio. And in model 2, oxygen to hydrogen is an 8:1 ratio. So how would you draw those models if instead of the atoms having the same mass, they have different masses? What can we draw for that? And I'm going to pause the video here. All right, so let's see how it went. Anybody want to offer up their answer for model A? I'm going to keep the dots the same way we did them before. So white dot or circle would be oxygen, and dark dot will be hydrogen. So does anybody want to come up and draw theirs? Yeah. Compound A. Black dot is 1. Okay, excellent. Thank you very much, Clayton. Nice. Does that work, though, in terms of the mass ratio? Is it 16:1? It does, doesn't it? 4 plus 4 plus 4 plus 4 would be 16. 16:1 in terms of oxygen to hydrogen. Huh? Did you have something different? What'd you have? Oh. Okay, okay, so nice. What do you have? Okay, I would say the difference though here with Kira and Jade. Sorry. But one thing I like about this one better is that hers, all the oxygens have the same mass. So when I compare between Model A and Model B, like, so in this first model that we have up here, the mass is 4 for the oxygen. So when we come down here, we should try to make the mass of oxygen the same. So what you had was you did this. So this is a separate drawing I'm going to share on here. That as 1. And it's going to be the same kind of concept we saw in the other idea, but instead it's just going to be 2 oxygens with each one being 8. Okay? So that would work out 16-to-1 ratio as well. All right? So it could be either one of those. This one would be O4 H1, or sorry, H. And then this one would be O2 H. Hey. Okay. Could I have just done, keep it simple like how we did yesterday, where we do just one of each, different masses, and work from there? Like, what if this is 16 and this is 1? That would be OH. Could have done that as also, right? So any of these options would really work. We're showing 2 things. We're showing different masses, and we're showing that there's a 16-to-1 ratio in terms of mass. Now, not to show favoritism, but I'm going to pick this student's model just because it's me. None of them are wrong. Nope. None of those are wrong. Just Jade's. Just kidding. Yours is actually right too. You just would have to keep it consistent to the next model. All right. So what I'm saying is this. All right, my one where I started off and I just made this one, and then I made a much larger one that was 16. Okay, and that's OH. How could I do model B that's supposed to be an 8-to-1 ratio if I'm using that? So if I have this, and I have this, keeping the masses the same again. Oh, you did. Yeah, I was going with this one. I chose my own model. Oh, sorry. Is there any way that I could alter this model so that it becomes an 8-to-1 ratio? Any ideas how to alter this? How can I change that to make an 8-to-1 ratio? This is different. It's confusing compared to yesterday's because yesterday we were just adding the larger ones because everything was doubling. But what happened in this scenario? Instead of doubling, what happened to the mass ratios from A to B? Yeah, it went smaller. It went down by half. What if I added another one of these? Now it's a 16-to-2 ratio. Is there another way to say a 16-to-2 ratio? 8-to-1. So I could do that too. What would the formula of this be? H, there are 2 of them. O, there's 1 of them. Ever seen that before? Water. So here's the thing, guys. When we talk about these 2 hypotheses, hypothesis 1 had some people mention it's just easier. I can see that there's like 4 of these and 3 of these, and I just draw the circles, piece of cake. But actually, when you look in terms of all the atoms being bonded together, that hypothesis 1 is very messy. It's not as clean. It's not as simple. And what we were looking at with Avogadro's hypothesis, when he was comparing how different atoms combine to form compounds, then he said they combine in simple whole number ratios. All right. So yeah, this hypothesis 2 is what we want to go with. Simple whole number ratios. 1-to-1 ratio, 2-to-1 ratio. So we are going to go with hypothesis 2. All right. So now we're going to get back to our groups. We're going to finish up that worksheet. And I just want to say that thank you. We're just going to say, and I want to tell you in part, the rest of this thing going some 3 and 4, you're going to find that those mass ratios aren't quite as easy to work with. Don't round any off either. You don't have to actually do the models here. You're just going to compare numbers and think about it and see what you think the answers are. And I'll be walking around group to group to see how you're doing. Okay? So let's get back to our groups and try to finish this worksheet.